So in the previous example, we integrated 1 to infinity 1 over x squared, and we got a finite area 1. Well, what happens when we do the integral from 1 to infinity 1 over x? So that 1 over x squared, when x is bigger than 1, x squared is bigger than x, so that graph actually looks like this. Comes down and crosses under the 1 over x. So when we found that area, we were finding the area of this infinite strip. That's a lower or smaller area than the integral from 1 to x. Okay, 1 to x is up here. So we want to know, well, what's this area? Is it still finite? I mean, before we got an area of 1. So we do the same thing that we did before. Since we got infinite interval here, we are going to integrate from 1 to b, 1 over x dx. And then we take a limit as that b goes to infinity. So antiderivative 1 over x, that's natural log. So this will be limit b goes to infinity. And then natural log absolute x. And we are taking and evaluating that from 1 to b. So this will be limit as b goes to infinity. And we'll plug b in. So that's ln of b. B is approaching infinity, so it's greater than 0. Minus, we'll plug 1 in. The absolute value of 1 is 1. So this is natural log of 1. And then natural log of 1 is just 0. So we're just taking the limit of natural log of b as b goes to infinity. Well, that's infinite. So that's saying if you find the area here from 1 out to infinity underneath the 1 over x function, you get an infinite answer. So here, area equals infinity. So that means that 1 over x squared goes down fast enough to give us a finite area here. So now if you're painting, you can't find enough paint to paint this infinitely long strip because area is infinite. Now this is kind of peculiar here because when we did 1 over x squared, go back up here, 1 over x squared, we got that 1. You see this strip goes down a little bit faster. It's not quite as high, less area there. So 1 over x, we get infinite area. So is there something in between the two of those that still gives finite area? What's the cutoff? If we do 1 over x cubed, that should also be finite. But what if we did 1 over x to the 1.5? So that's something to wonder about. So we'd like to know here, when is the integral from 1 to infinity of 1 over x to the p dx finite? Now the terminology here, if this is finite, if this integral is finite, we say it converges. Like a limit converges. So a limit does converge to an actual number. And when you get an infinite area here, we say that the improper integral diverges. So it's misbehaving. It's marching off to infinity. And the answer of when this converges and when it diverges comes in what's called the p-test. This is actually a theorem, and it says if you're integrating from 1 to infinity 1 over x to the p power dx, that converges. So that means that it's finite. You get an answer that's less than infinity if p is greater than 1. And it diverges, so that means your answer is equal to infinity if p is less than equal 1. So 1 really is the cutoff. So for example, we know that integral from 1 to infinity of 1 over x to the 5th dx, that's going to be finite by the p-test. It converges. So that one we can use our limit definition for improper integrals and actually compute it. However, if we were going to do the integral from 1 to infinity of 1 over square root of x, so that's x to the 1/2 power, that's p less than equal 1, this one is going to diverge. That's going to give infinity for an answer. So, and this will come in handy just, looking at improper integrals to try and gauge whether they're going to converge or diverge. This theorem doesn't give the exact answer when they do converge, but it does give us an idea of whether or not the answer is infinite.